So the theme of these two lectures is going to be describing ensembles of Hamiltonians. And some of the mathematics that's been used recently in the theory of topological superconductors and topological insulators, in particular the famous periodic table of topological superconductors and insulators. Actually, a lot of this mathematics goes back to a subject called random matrix theory. I'll try and write bigger. Random matrices entered physics in the 1950s. Sorry, I couldn't resist. Where experimentalists were scattering slow neutrons plus heavy nuclei like thorium, uranium. And what they found were thousands of resonance lines. Very complicated physical system. And Wigner had the bright idea that, well, look, it's going to be hopeless to solve for these resonance lines. Instead, let's study the statistics of these as energy levels of a random Hamiltonian, of a Hamiltonian pulled out from a distribution of an ensemble of Hamiltonians, with some probability distribution. And Dyson took up this problem in a series of papers. And in particular, in 1962, he wrote a paper called The Threefold Way. And a great deal of today's lecture is going to be explaining Dyson's paper from 1962. The main point of the paper, you see, was that yes, you could get a natural probability distribution on ensembles of Hamiltonians, but the probability distribution you actually get depends very much on the symmetries in the problem. So I'm going to be trying to explain Dyson's paper from way back then in such a way that the generalization to the tenfold way that we see in the periodic table of topological superconductors and insulators is not too unnatural. So here's a roadmap of the talk. So I'm pretty much done with the overview, except to go through the roadmap. And so then I'll start talking about states and projectors and very basic aspects of quantum mechanics and symmetry, just so we're all on the same page. And then I will be led to something called a Z2 graded group. And we'll want to understand the representation theory of Z2 graded groups, which is pretty much like ordinary representation theory. But to understand it properly, we need to do a little bit of linear algebra, which is regrettably not often taught in physics courses. So I'll review real complex and quaternionic vector spaces and the relations between them. And then we'll talk about what it means to be compatible with the dynamics. So the word symmetry is a very vexed word in this subject. So I'm just talking about certain groups which are compatible with the dynamics. Then we'll be all set up to do Dyson's threefold way. And if there's any time, which there won't be, I'll show you how to add a gap to the argument. Okay, so let's get started. Let's not get started. I still want to say one more thing in the overview about Dyson. So just to give you the main punchline right at the beginning. So usually we start with a Hamiltonian, and then we find the symmetries. What Dyson did is he turned the problem on its head. He said, let's start with the symmetries and then find the compatible Hamiltonians. So those are going to be the ensembles of Hamiltonians. All right, so that's the punchline. That's what we'll get to in Dyson's threefold way. All right, so now let's finally start with number 2. So in our courses in quantum mechanics, we're often taught that states, which we learn later are pure states, are vectors psi in a Hilbert space H, which are normalizable. And then because they're normalizable, we're told to normalize the wave function. And then we're told, well, actually, if psi 1 is equal to z psi 2, where z is a phase, then those represent the same physical state. And all of that's perfectly true. But I want to now rephrase exactly that statement in a more geometrical and conceptual way. So to every normalizable state, we can associate a rank 1 projection operator. I'll just call projector for short. So let's call it p psi. Using Dirac's notation, that would look like this. Okay, so you see that is a projection operator. P psi squared is p psi. It's Hermitian. And the image of p psi, which I might call L psi, is a line in Hilbert space. By a line, I mean a one-dimensional subspace of Hilbert space. Okay, so we see that there's a one-to-one correspondence between the set of lines in Hilbert space with rank 1 projection operators with normalizable wave functions modulo the equivalence I just mentioned. Indeed, notice that P of psi is equal to P of z times psi if z is in C star. So let's give this common space a name, the projective Hilbert space. And this is what pure states are. The set of pure states in a quantum system described by a Hilbert space is the projective Hilbert space. Now, in quantum mechanics, we all talk about probabilities. That's what we observe. We measure probabilities. Now, probabilities come down to overlaps, and usually we write the overlaps this way. But if we want to think in terms of projection operators, let's write it this way. Okay, so to a pair of projection operators, we get an overlap, the trace of the product of the projection operators, and that defines a function. I'll call it the overlap function from the projective Hilbert space times the projective Hilbert space to real numbers between 0 and 1. Okay, now, pH, projective Hilbert space, has a natural Riemannian metric. I'm not going to describe that metric for you in detail, but I'm just going to work through one important example to show you the metric and show you what the overlap function looks like in terms of that metric. You see, the overlap function has a very beautiful description in terms of that metric. The overlap of, let's say, P1 and P2 is the square of the cosine of the distance from P1 to P2 in this natural metric divided by 2. So let's check this formula in a special case. And the special case, this is my example, will be a 2-qubit system. A 1-qubit system. Anyway, it's H equals a 2-dimensional complex Hilbert space, whatever you want to call it, and a normalizable vector, psi, will simply be a column of complex numbers. And so the norm squared will be the sum of z1 squared plus z2 squared, and that's not 0. And because it's not 0, we can do what our teachers told us to do, normalize it. And if we normalize it, we get what I'll call the unit sphere in Hilbert space. That's the set of psi with norm 1. Okay? And now notice that if you took z1 and you wrote it in terms of its real and imaginary parts, and z2 and you wrote it in terms of its real and imaginary parts, this equation that z1 squared plus z2 squared equals 1 is a sum of 4 squares equals 1, and that's the equation for a 3-dimensional sphere in 4 dimensions, 4 real dimensions. So this you can think of as a 3-sphere. So now let's ask, what is the corresponding projector to a state psi? Well, a pure state, of course, is a special case of a density matrix. So as a sort of side exercise, let's just work out the most general density matrix and then make it into a projection operator. So first of all, a density matrix is a Hermitian 2-by-2 matrix. And I think several lectures in this school have mentioned that this is the space of 2-by-2 Hermitian matrices where A and B are real. So, for example, in Professor Witten's lecture, he was stressing the fact that if you want eigenvalues to be the same, you have to set 3 real numbers to 0, this B. Indeed, the density matrix has to be non-negative. So what are the eigenvalues? Well, of course, you could rotate this to the sigma 3 direction. So the eigenvalues are A plus and minus the norm of B, and that's got to be greater than or equal to 0. And then finally, we need the trace of rho to be 1. And so that implies that the general density matrix is of the form 1/2 1 plus x dot sigma, where the norm of x is less than or equal to 1. In other words, we can identify the space of all density matrices with the 3-dimensional ball. Okay? Now, as I said, in this lecture, states are going to mean pure states, so we got to make this thing into a projector. And so it's an easy exercise. You can do it right now if you're bored. This is 1 plus x squared over 2 plus x dot sigma. Okay, so that means that this is going to equal rho if and only if x squared is equal to 1, which means that the pure states, pH, is a copy of a 2-dimensional sphere. It's the extremal states on this convex set of density matrices. Okay, good. So to every element, to every vector, normalizable vector, we can normalize it to 1, and then we get a projection, I'll call it pi, to the pure states, to the projective Hilbert space, which we've identified with S2. But how exactly do you write that? Well, okay, so the general normalizable unit norm vector can be written as a unitary matrix times 1, 0. And the unitary matrix, I'll take it to be special unitary, because I can. So I can write that as, in terms of Euler angles. And then you can do one of two things. You can either expand this out. C is for cosine. S is for sine. And then you can take the outer product of psi with psi, or a slightly better way to think about it is you could say, well, okay, if psi is u times this, then p psi is u times the projection operator associated with this state here, 1, 0. But what's that? That's clearly 1 plus sigma 3 over 2. So we could say it's that. And then you should know that this is equal to 1/2 of 1 plus n hat dot sigma, where n hat is the unit vector with the usual Euler angles, spherical angles, theta and phi. Okay, so that's the map from states to projection operators. But now what we've gained from this is we can calculate that overlap function very nicely. So the trace of p psi 1, p psi 2, again, a very quick exercise, is 1/2 1 plus n1 hat dot n2 hat. Okay, so if this one is n1 hat and this one over here is n2 hat, then they're separated by some angle, let's call it delta omega. And you see this is equal to the cosine squared of delta omega over 2. Now, I told you that pH has a natural Riemannian metric. And that's crystal clear in this example because the unit 2-sphere has a natural Riemannian metric. It's the round metric. And what is the distance in the round metric? It's the angle between the two vectors. So I have just checked this formula in the case of a two-dimensional Hilbert space. And I hope this demonstration makes it very believable that it's true in general. Now, at this point, I have to exert a great deal of self-control because there's some really beautiful topology associated with this and with its generalization to n dimensions, which I will not explain. And it's actually related to a classification scheme that Kataev has for short-range entangled invertible ground states. And so all that is being skipped for reasons of time. Yes. Now, having done this example, I want to add in now the concept of symmetry. So let's begin with a definition. The group of quantum automorphisms. And automorphism is a fancy mathematical term for sort of, self-equivalences of any mathematical object. So the group of quantum automorphisms is the set of, well, it's a group, and I'm denoting it by this fancy symbol. And all it is, it's the set of maps from pH to pH that preserve the overlap function O. In other words, if I have two projectors and I act with F bar, let me use a different color. If I act with F bar on this guy and F bar on this guy, and I get O of P1, P2, that's what it means to preserve overlaps. And clearly I can compose these functions. They're going to be invertible. And so that's a group, the group of quantum automorphisms. So, for example, question? Oh, yeah, right. Okay, so how's that line? You see that line? Okay. Okay, so for example, H is, if H is C2, then our group of quantum automorphisms of pH is, well, we just proved that the overlap function comes down to the distance, and so the group of automorphisms should be the isometries of the two-sphere. What's the group of isometries of the two-sphere? It's O3. All right? Now, this is all very well and good, but you see, we have a nonlinear space here. We have the two-sphere as our space of pure states. If we went to higher dimensions, we'd have to talk about complex projective space. So it's better to work with linear transformations, and that's where Wigner's theorem comes in and saves the day. Okay, it says that every quantum automorphism is induced by a unitary or anti-unitary operator on H. Now let me explain what all that means. So let's begin with the unitaries. So the group of unitary operators on Hilbert space, I'll denote it as U of H. Suppose I have U, which is in U of H. Then I need to get a quantum automorphism, and I'll call it F bar sub U, and it has to take projectors to projectors, and all it does is it takes P and it conjugates it by P, by UP U dagger, because U dagger is U inverse. This is another rank 1 projection operator. Okay, so that's good. So now what about the anti-unitaries? Well, that takes a little bit more work. So first, let's begin with an anti-linear operator, and then we'll say what an anti-unitary operator is, and then we'll be ready. So, definition. A map, let's say O from H to H, is, strictly speaking, C antilinear if, well, it certainly preserves sum of vectors. Okay, so it takes O of psi 1 plus psi 2 to O of psi 1 plus O of psi 2, no problem. But if I multiply by a complex scalar, it complex conjugates the Z. Okay? And then we'll say it's anti-unitary if it also preserves norm. So if O of psi has the same norm as psi. Okay, now a little exercise. Let's define the adjoint of an anti-linear operator this way. Okay? A little different from the way you define an adjoint of a C-linear operator. And then show that if O is anti-unitary, then indeed O dagger is the inverse of O. So if we have an anti-unitary operator A, then we also have a map on projection operators, rank 1 projection operators, that looks like that. You see, you might worry, is this still a projection operator has to be C-linear? But this is C antilinear and so is this. So the net thing is actually a C-linear operator, and in fact, it's a rank 1 projection operator. Okay. Now, the set of all unitary and anti-unitary operators is a group. So let me call ought sub r of the Hilbert space, that's the group of all unitary and anti-unitary operators. You see, if you compose two unitary operators, it's unitary. If you multiply a unitary and an anti-unitary operator, it's anti-unitary. These are little exercises. If you multiply two anti-unitary operators, it's a unitary operator. So the whole set of unitaries and anti-unitaries forms a group, and I'll call that group ought sub r of h. And so what we demonstrated before, or what I've just demonstrated here with these f bar sub u's and f bar sub a's, is that there's a projection from here to the group of quantum automorphisms. Okay, so the content of Wigner's theorem is simply that this is surjective. So what mathematicians write is an arrow like that. That just means that the map is surjective. Moreover, this pi is a homomorphism. It's a group homomorphism. That should be clear from the definitions. If I compose f bar sub u1 with f bar sub u2, that's f bar sub u1, u2, and similarly from f bar sub a. So pi is a homomorphism, so I can ask, what is the kernel of pi? Well, clearly, if I take the unitary operator to be multiplication by a phase, that will commute with the projection operator and it will cancel out. So those operators, let's call them O sub z, which takes psi to z psi. These operators are clearly in the kernel, and in fact you can show that it is the full kernel. Any other non-trivial operator will not commute with some projection operator. Now, this is clearly isomorphic to the group of phases, U1, and henceforth, this notation is way too heavy, so I'm going to call this O sub z just z. Okay? So, going back over here, the kernel of this pi is the group U1, and that certainly injects into here. That's what the 1 here means. And this is what mathematicians call an exact sequence. It means that the image of this group homomorphism is the kernel of this group homomorphism. So what does that look like in our example of the two-dimensional Hilbert space? Question? Pardon? Oh, dear. Okay, so that's important. Can you see that? Yes. So I can shorten this arrow. Yes, it's a shorter exact sequence, indeed. Right. So now let's see what's going on here with our two-dimensional example. So as I said, ought R of H, it's the unitaries, disjoint union the unitaries times the complex conjugation operator. You see, the complex conjugation operator is an anti-unitary operator on C2. It does not have a matrix representation. That's okay. It's antilinear. It couldn't possibly have a 2x2 matrix representation. Okay, this is the full group. And then we have this pi here. And we had ought quantum of pH. And we said that this was equal to O3. And O3 is SO3, disjoint union SO3 times any parity operator you like. You could take a reflection in any plane. You could take inversion of 3 spatial coordinates. So what does this map pi very explicitly? Well, O is unitary or anti-unitary, of 1 plus n hat dot sigma. O inverse, or O dagger, it's the same thing, is 1/2 1 plus some other vector on the sphere. Oops. And the map, pi, takes this unitary or anti-unitary to the map, which takes n hat to n hat prime. Now, these guys, the unitary guys, go over here to proper rotations. And these guys go over to the improper rotations. So, for example, if you take C to be, if you just take O to be C, the complex conjugation, that goes to reflection in the plane orthogonal to y hat. Okay, so that means over here that we have a homomorphism, phi, which measures whether we're in the unitary or the anti-unitary component. So that goes to Z2, which I'm thinking of multiplicatively. And similarly, there's a homomorphism here, which I'll call phi prime, which also measures whether this is in a component connected to the identity or not. And this diagram commutes, namely this phi here is the composition of pi and phi prime. Now, I want you to notice one thing about this sequence here. If I take O times, remember the operator, this is an operator, this is the operator of multiplication by a phase. Okay? This is not O sub z, this is O times z. And so this is z to the phi of O times O. In other words, it's ZO if phi of O is 1, namely it's unitary, and it's Z inverse O if phi of O is minus 1. But Z inverse is the same as Z complex conjugate. Right. So now suppose that there's a symmetry in our physical system. Okay? So far, these groups are sort of the universal symmetry groups of quantum mechanics. They are the groups of potential symmetries. If I have a crystal, it obviously isn't going to have the full group of quantum automorphisms as a symmetry. The crystal breaks lots of symmetries. It leaves a crystallographic symmetry. So my crystallographic symmetry might be some group G bar, and to say my physical system has a group of symmetries preserving probabilities means there's a homomorphism, let's say G bar, into this group of potential symmetries, let's call it rho bar. Now, when you have this kind of situation, mathematicians will come along and tell you that there's a tautological universal construction of another group, let's call it G, together with a homomorphism pi prime and rho, such that this diagram commutes. And as with all tautological constructions, the construction of G is completely stupid. It's G is the set of pairs of G bar and O such that rho bar of G bar is pi of O. Okay? And you can check. That's a subgroup of G bar times aught quantum pH. Okay? And what is pi prime? Pi prime is just map onto the first component there. And therefore, the kernel of pi prime is again exactly the same U1, like this. Okay? So, and by construction, this is onto. Okay, so when we have a group of symmetries of our physical system, the thing that acts on our Hilbert space is this G, which sits in this exact sequence. Okay, so for every physical symmetry, there's a whole U1 rotation of possible operators that we can realize that symmetry by. Now, just the way we had this equation here, we similarly will have a g dot z is z to the phi of g. Let's call it phi double prime of g. Is it g? So that's going to be z g or z inverse g, depending on whether phi double prime of g is plus 1 or phi double prime of g is minus 1. What is phi double prime, you ask? Well, you see, when I have this situation, I can compose these two and get a homomorphism phi double prime. And I can similarly compose these two and get a homomorphism phi triple prime. And the notation is clearly getting completely out of hand. So now I'm just going to say phi. Okay? And when I say phi, you will understand which one I mean by which group I'm talking about. So indeed, let's introduce some useful terminology at this point. I'll say a group G with a homomorphism phi from G to Z2 is a Z2 graded group. That's all that means. Okay, so item number 4 is going to tell us about representation theory of Z2 graded groups. And when I have this kind of sequence, let me not write it again. Let me say the sequence on top there will be called a phi-twisted central extension by U1. Okay, so I heard lots of lecturers using the term central extension, so that means you all know what a central extension is. It means that there's a subgroup here, which is in this exact sequence and is in the center. But you see here it's not in the center. Why is it not in the center? Anybody? Right, because sometimes the Z comes through the G and gets complex conjugated. But it's almost a central extension. It just gets complex conjugated. So it's called a phi-twisted central extension. So this is all very abstract. So let's do an example. So the simplest example you can think of is to take the group group Z2, not G2. G2 is certainly not the simplest example of a group. And I think this is my boundary. Okay, so let's take the group, let's call it M2 bar, which has 2 elements, 1 in T bar, and the group law is T bar squared is 1. And now I'm going to make it a Z2 graded group by saying phi of T bar is minus 1. Okay, so now the question, what are the phi-twisted central extensions? Okay, so, well, they have to look like this. There are going to be 2 of them, exactly 2. I'll call them M plus and M minus. Okay, and so what do I know about this central extension? So T bar has to have a preimage. Let's call it T. But since T bar squares to 1, that means that T squared has to go to 1. But this is an exact sequence, so T squared had better be in the image of this. That means it has to be a phase. What does that mean? Well, let's look at T cubed. So T cubed is T times T squared is T times Z is Z inverse times T, because t has the odd grading. But t cubed is also t squared times t, which is z times t. Z is a phase, and so that implies that z is plus or minus 1. Now you might ask me, wait a second, there's not a unique lift. What if you had chosen instead, it's another color, what if we had chosen instead t prime is mu times t, where mu is a phase? Would I get a different sign? Well, let's check. So look at t prime squared. That's mu t, but t has odd grading, so that's mu mu inverse t squared. So indeed, there's an invariant here. The sign of t squared does not depend on what lift I choose. And so therefore, our group, our possible phi twisted extensions, M2 plus and minus, is the group of phases times t such that zt equals, such that tz is z inverse t, and t squared is plus 1 or minus 1. And the grading on this group is that phi of z is even and phi of t is odd. So let's draw a lesson from all of this. The lesson is that groups in quantum mechanics preserving probability are Z2 graded and act on Hilbert space through phi twisted U1 central extensions. Okay? So now the next thing we ought to do is talk about the representation theory of Z2 graded groups. And as I said before, in order to talk about that representation theory, I need to review some linear algebra, which some of you might know and some of you might not know. My experience at Rutgers is that the students don't know it, and so I have to teach it. So I'm going to review that material. So the material is about real, complex, and quaternionic vector spaces. Okay, so I trust you all know what a vector space is. So there's some axioms. You start with a field and you have vectors and you know how to multiply scalars times vectors to get another vector. Now for us, the field is always going to be the real numbers or the complex numbers. That's plenty. And the distinction between a real vector space and a complex vector space is going to be very important to us. So it might sound like a splitting hairs, but actually it's a pretty important distinction. So you see, in a real vector space, so I'll write R vector space, you know how to multiply real numbers times a vector, but you don't know how to multiply the square root of minus 1 times a vector, because it's just not there in the axioms. It has no meaning. But we have a definition. Okay? Let V be a real vector space. Then a linear transformation I from V to V such that I squared equals minus 1 is called a complex structure. And the reason it's called a complex structure is that to this pair of data, V and I can now make a complex vector space. I have to tell you how to multiply a complex number z times a vector v. Well, suppose z has real and imaginary parts, x and y. Then I define this to be x times v plus y times I of v. And you see, now it just behaves the way multiplication by a complex number ought to behave, because I is linear and I squares to minus 1. Now, for simplicity, for those who know all about this stuff, I'm going to assume that v has a Euclidean metric, and I'm going to take I to be an orthogonal group, and I can do this without loss of generality. That's without loss of generality, not with loss of generality. So let's do an example. Let's take v as r to n, and then we could take I naught to be 0, minus 1, and like that. Clearly, that matrix squares to minus 1. But, and this is part of the point of what I'm saying, that's not the only complex structure. We can make other ones. Indeed, if I is a complex structure and S is an orthogonal transformation, then clearly SI, S inverse, is also a complex structure. Right? Take a second to square that and check that it squares to minus 1. Now, here's a little lemma. I should say I'm not proving anything in these lectures. There's no time. However, there's a link to the notes on the PiTP lectures, on the PiTP homepage for my lecture notes. Now, if you actually take the trouble to read the first paragraph of those lecture notes, you'll see that there's another link to notes for a course I taught at Rutgers. And that's 250 pages. And it has all the proofs. I proved absolutely everything, those poor students. And I proved everything, and it has lots more examples. So, for example, you'll find a complete proof of the statement I'm about to make there. So you can show, including, by the way, a proof of Wigner's theorem. Nobody asked me, how do you prove it? Okay? There are 46 proofs in the literature. I give in my lecture notes a streamlined version of a proof by Barkman. There's a very beautiful recent proof by Dan Fried. It capitalizes on this relation of the overlap to the distance function in isometries and things like that. Okay, anyway, back to this. So you can show that for all complex structures, there exists an orthogonal transformation such that SI, S inverse is I naught. That means that the orthogonal group acts on the set of complex structures, and not only that, it's a homogeneous space. You can get from any one complex structure to another. And so the complex structures, let's see, I want to save this, so let me put this over here. And this is the visible region. This is the horizon. Okay, yeah, okay. What? A little more to the left? Okay, that's the ergosphere. All right, so the set of complex structures on R2n, well, it's a homogeneous space for K, where what is K? K is going to be the stabilizer of I naught. So it's going to take SI naught, S inverse equals I naught. Now, a moment's thought will show you that that's the set of orthogonal matrices that look like this. Okay, now if we allowed ourselves to conjugate by unitary transformations, you see that's the same as matrices that look like this, basically because because I sigma 2 can be conjugated to I sigma 3. And if this is going to be orthogonal, this had better be unitary. And if I know this unitary, then I know that unitary. So K is isomorphic to UN. And indeed, this is a way of embedding UN in O2N. Okay, so that is complex structures on real vector spaces. Now, let's do another kind of structure. Suppose, this is 3b. Suppose that V is now a complex vector space. Please note the change of notation. I can't invent a new letter for every new structure, okay? So you have to understand the notation locally. So V is a complex vector space. So then, of course, I could define V sub r, which is the same set as a real vector space. I just forgot how to multiply this by the square root of minus 1. It's still a vector space. And so now the dimension as a real vector space of V sub r is twice the dimension as a complex vector space of V. That's one way to get a real vector space out of a complex vector space, but there is another way. Definition. If V is a complex vector space, then a C antilinear operator O from V to V such that O squared is plus 1 is called a real structure. Okay? And when I have a real structure on a complex vector space, then I can define V plus to be the fixed points of this O, namely the set of vectors V such that OV is V. Notice that this V plus is really a real vector space. You see, if O of V is equal to V, then O of I times V is minus IV. Okay? So multiplication by the square root of minus 1 takes you out of V plus. So you can only multiply vectors in V plus by real numbers. So let's do an example. Let's take V to be the one-dimensional complex vector space. Then V sub r is the plane R2 as a two-dimensional real vector space. And the most general anti-unitary O takes a complex vector x plus iy, and it complex conjugates it, and it multiplies by e to the I phi. That's the most general anti-unitary operator on a one-dimensional complex vector space. And what's V plus? Well, V plus is going to look like this. It's going to be the line at angle phi over 2 from the x-axis. As I hope you could check quickly. And you see, this is, as advertised, a one real dimensional space. But it should be clear from this example that just as there was a whole space of complex structures on a real vector space, there's a whole space of real structures on a complex vector space. Indeed, if I'm given a basis, okay, E sub I for my complex vector space V, I can define a canonical real structure by complex conjugating the coefficients in that basis. Now, if I map one basis to another by a unitary transformation, then I'll get a different real structure. So just the way we had a group acting on the space of complex structures, we also have a group acting on the real structures on complex vector spaces, and that group is just taking one basis to another. You can show that this is the most general real structure. In fact, that's kind of obvious. You see, you take the V plus as the fixed points and V minus the anti-fixed points, and that gives you the whole space. And what is going to be the stabilizer? Well, the stabilizer is going to be the unitary transformations which preserve the complex structure, and those are going to be real orthogonal transformations changing this basis. So now, you see, we have a space of real structures on Cn, which is this homogeneous space Un mod On. Right, so now to the next topic is to go to the quaternions. Okay, I need a definition first. An algebra over a field kappa. I'm always going to use kappa for reals or complex numbers, is a vector space over kappa with a kappa bilinear map. Let's call it mu. This is the multiplication of vectors to get a new vector. Okay? Now, usually we make the notation a little less heavy. Instead of mu of v1, v2, we just write v1, v2. Now, as a little exercise, notice that given in algebra A, there's always another algebra we can define called the opposite algebra, where mu op of v1, v2 is the old mu of v2, v1, and that's another algebra. And it might or it might not be isomorphic to the original algebra. Okay, so that's an algebra. Actually, let me use this. Question? No? Okay, so the quaternion algebra which I'll denote as H, is R4 as a vector space over R with a basis. Let's call it 1, I, J, K, such that I squared equals J squared equals K squared is minus 1. I times J plus J times I is 0, and cyclically, and that's it. So this is associative, I should have said. All the algebras in these two lectures are going to be associative, but it is not commutative. And you can see that right from this equation here. I and J don't commute, they anti-commute. Now, the quaternion algebra has a conjugation operation. So if I expand a general quaternion in terms of its basis, then Q bar is, well, I just flip the sign of I, J, and K, but not of the unit. Okay, and then you can check that Q bar is Q bar Q is the sum of x mu times 1. Now, that's good because now that we have a notion of conjugation, we can define a notion of the unitary group. Indeed, there are a number of exercises in the PiTP notes which are intended to make you familiar with the quaternions if you haven't seen them before. And one of the things you show in those exercises is that you can define the group of n by n unitary matrices over the quaternions. So what does that mean? So they are, as I just said, n by n matrices with quaternion entries. And you see, U dagger makes sense now because I certainly can transpose a matrix, and then I use quaternion conjugation on the matrix elements. Now, if you are recalcitrant and refuse to think about quaternions, you can think in terms of complex numbers. And this is isomorphic to the unitary symplectic group 2n, which is the unitary matrices which are 2n by 2n. So let me stress that it's complex unitary matrices, such that U star is equal to J U J inverse. And because of the definition of a unitary operator, this is the same as unitary intersect symplectic U transpose J U is J. And what is J? J is 0, minus 1, 1, 0. It's the same as I naught before, but I didn't call it I naught because it's conceptually different. Question? So the quaternions is an extension of the complex numbers. That is correct. So you see there's a subalgebra of H where I just take x1 times I plus x4 times 1. But there's another embedding of the complex numbers where I take x2 times j plus x4 times 1. And in fact, there are many embeddings. They're parameterized by a two-dimensional sphere.
So how much higher can you extend?
Great question. Great question. So there's a wonderful, so the question is, how much higher can you extend? Yeah. Again, I'm going to have to exhibit some self-control. This is exactly the question that stumped Hamilton for 10 years. He was trying to find an algebraic description of rotations that was analogous to the geometrical interpretation of complex numbers in terms of rotations in the plane. And the famous story of his vandalism of a certain bridge in Dublin is when he figured out that he had to go to 4 dimensions. Now, immediately after that, several people started asking this question, and a man named Graves, and then later a man named Cayley, realized that you could actually extend this at the price of losing things you know and love. So the next extension is called the octonions, and you lose associativity. But there's something called the Cayley-Dickson process where you can just keep doubling, 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 and at each stage, the algebraic structure gets more and more complicated. Okay. Another question. Sorry? That's true. Yeah. Let's see. There are various associator relations. Now, all algebras in these lectures are going to be associative. I don't want to get into non-associative algebras. Yeah. Okay. I do not want. I'm so sorry. Non-associative algebra. Well, let's not go there. We're only going to be dealing with associative algebras. Interesting questions. I hate to quash it, but we've got a lot of other stuff to do. And why is it that we're only going to be looking at associative algebras? Because you see, I'm interested in operators and representations and various kinds of operators on group representations and so on. And you see, if you have well-defined operators acting on some Hilbert space, that's always going to be associative. Okay, so back to the exercises. So this is the content of one of the exercises. And another thing which will be useful to know is that, you see, the quaternions act, as any algebra, acts on itself by left and right multiplication. So the left multiplication operator takes a quaternion q prime, say, to q dot q prime, and the right multiplication takes q prime to q prime dot q. So the set of these operators forms an algebra of linear transformations of R4 to R4, which is isomorphic to H. And the set of these operators is another set of linear transformations of R4 to R4, which is H opposite, because you're multiplying on the right, not the left. If you actually do the multiplications, you'll see that. But this is actually isomorphic to H. And notice that these two algebras of operators inside the algebra of 4x4 matrices commute. And in fact, part of the exercise is to show that H times H opposite is isomorphic to the full algebra of 4x4 real matrices. That's my notation for that. And that'll be useful in lecture 2 if we get there. Okay. So now I'm ready, having reviewed the quaternions, I'm ready for a definition. A quaternionic vector space is a real vector space, V, with 3 complex structures. Let's call them R, C, and H. Oops, excuse me. Going on autopilot there. 3 complex structures, I, J, and K, which satisfy the relations of the quaternions. I squared equals J squared equals K squared equals -1, and IJ plus JI equals 0 plus cyclic. Okay, I hope I didn't confuse people. Some wires got crossed in my brain when I wrote RC and H. There's another, that's going to be the threefold way, which is coming up. But that has nothing to do with what I'm writing right here. A quaternionic vector space is a real vector space with 3 complex structures, I, J, and K, which satisfy the relations of the quaternions, which are still on the board. What's an example? An example would just be take column vectors of quaternions. So that's the real vector space R for n, and use component-wise multiplication by I, J, and K, say on the left. Okay? Okay, so now we had complex structures on real vector spaces. We had real structures on complex vector spaces. Now we're going to have a quaternionic structure on a complex vector space is a C antilinear map. Let's call it J from V to V, such that J squared is -1. And the reason we call it that is that the underlying real vector space has a quaternionic structure. I is the square root of -1. We know what that means because it came from a complex vector space. J is given to us by the definition, and then K is equal to I times J, and then you can check that indeed these 3 operators satisfy the algebra of the quaternions. So now there's an analogous discussion to what I gave here, and because of time I'm not going to go through it in detail, but we again will have a whole space of H structures on C2n. Notice you have to have an even dimensional complex vector space. So this is equal to U2n mod USP2n. And similarly, we can talk about complex structures on Hn, and this is equal to USP2n mod UN. So,
Does it make sense to talk about real structures?
yeah, it does, but I'm not going to need that. So these spaces here are examples of Cartan symmetric spaces. Symmetric spaces. And one of the reasons I went through this, aside from the fact that we need this linear algebra, is that these four Cartan symmetric spaces play an important role in the tenfold way in the Outland-Zernbauer classification of free fermion Hamiltonians. In a word, the tangent space at the origin of these spaces, that tangent space is a linear space which will be a space of free fermion Hamiltonians. So we've got 4, we've got 6 more to go. Okay, now I want to go back to the main development. We were talking about Z2 graded groups. And remember, we had this story here. So let me get myself some blackboard room. We had that whole story about Z2 graded groups. And now we had the lesson, which I should probably not cover up. So because of this, we now want to talk about the representation theory. Of G and phi. So, let's begin with a definition. A G phi rep, which I'll denote V and rho, is a complex vector space, V, with a homomorphism rho from G into the real linear transformations, such that if I think of it as a transformation on a complex vector space, it's C linear for phi of G is +1, and C anti-linear for phi of G is -1. Okay, so if I've got the data of a Z2 graded group, I have this notion of a G phi representation. And a lot of the representation theory of groups goes over pretty much word for word for G phi representations. Now, for example, an important definition is an intertwiner. So an intertwiner, O is a C linear map. Let's say it goes from V1 rho 1 to V2 rho 2, O, such that it commutes with the group operation. So if I first act with the group here and then do O, that's the same as acting with O and then acting with the group. So mathematicians will write down a commutative diagram. You see, I can act with a group that's rho 1 in the first representation of G, and then I can apply O to get over to V2 rho 2, or I could apply O to get over to V2 rho 2, and then apply the second representation. And so that commutes. And I'll denote by hom sub C, because they're C linear, upper G, because they're G invariant, V1, V2, the set of all intertwiners. Now, the one thing I want to stress here is that this is a real vector space. Why is it a real vector space? Well, you see, if O is an intertwiner, and I ask, is I times O an intertwiner? Well, maybe not, because if I act with rho 2G times IO, that will be minus IO times rho 1G if phi of G is -1. Okay? So if my grading on the group is non-trivial, then this is only a real vector space. Question?
This row, does it have to map into the endomorphism of V, or is it really just the automorphism?
Very good. Yes. Well, it's true that it goes into the endomorphisms, but a finer statement is indeed true. Because it's a group, it has to be invertible, so you're quite right.
Is there a reason you're not allowing intertwiners to be C anti-with?
Yes, because the intertwiners that I'm going to be interested in are Hamiltonians. And Hamiltonians are going to be linear operators. Okay, I'm just taking that, if you like, as an axiom. So our strategy in getting to the Dyson threefold way is that our ensemble of Hamiltonians is going to be, first of all, a set of Hamiltonians that are intertwiners in an appropriate sense. And because Hamiltonians are C-linear, that's why I want to take intertwiners in this definition to be C-linear. Yes, question? Sorry, here? So the question is V real or complex? It says it's a complex vector space V.
Okay, why is it V sub R?
So because otherwise, if I had tried to write V, that would mean C-linear operators. So it's linear as an operator on the underlying real vector space. But exactly because it can be antilinear, I can't drop the R here. Any other questions? All right, let's do an example. Of representations of some Z2 graded groups. And which ones? Well, of course, the ones we used as our examples before. So let's take M2 plus. So you remember that was an extension by U1, a phi twisted extension. And the important thing was that there was a T in here, which squares to 1. So what's an M2 plus representation? M2 plus is Z2 graded by that equation there. So an M2 plus representation is a complex vector space, together with a row of T, which is antilinear, and row of T squares to 1. Have you seen that definition before? Just a few minutes ago, I called this a real structure. Okay? So a phi representation of M2 plus is nothing more or less than a real structure on a complex vector space. By the same token, if we take M2 minus, well, we have now row of T is C antilinear, and row of T squares to minus 1. So that was my definition of a quaternionic structure. So a M2 minus representation is a complex vector space with a quaternionic structure. Notice, by the way, that implies that V as a complex vector space, if it's finite dimensional, has even dimension. This should remind you of the time reversal operator on electrons, and the fact that the dimension here is even as a complex vector space is a version of Kramer's theorem, that there is an even degeneracy. All right, so as I said, Most of the representation theory of Z2 graded groups is completely parallel to ordinary representation theory. You can define unitary representations, you can define sub-representations, reducible representations, irreducible representations. The one place where things are different is in Schur's lemma. Okay, so to state it nicely, I need a definition. A division algebra is an algebra A such that if A is not 0, then A inverse exists. So now let's state Schur's lemma. Let's see, how am I doing for time? Not good. I started, 10 minutes? Yeah. All right, well, so much for the tenfold way. But we'll get to the threefold way, I promise. Yeah, so let me put it here. So what's Schur's lemma? Well, it's always put in two statements. So an intertwiner between two G phi irreps is either 0 or an isomorphism. Statement 2 says that if I look at Hom sub C upper G of VV, this is equal to a real division algebra. Okay? And what's the proof? Let's do the proof of 2. That's easy. So you see, if you have an, if V is irreducible. Okay, so what's the proof? If you have an intertwiner, okay, from V to V, let's suppose it's not 0. Okay? If it's not 0, its image inside V is a subrepresentation. If V is irreducible, that must be the whole representation, right? If the image is the whole representation, the kernel must be 0. If the kernel is 0, it's invertible. QED. So that's the proof of Schur's lemma. Now, then we have another theorem, a very beautiful theorem, which I won't prove, but it's proved in those notes, that there exist precisely 3 real associative division algebras. And you know them all. It's R, C, and H. And that is the 3 of the threefold way. So let's do a quick example. So example 1. Let's take our friend M2 plus. What is an irreducible representation? Well, I can take it to be the one-dimensional complex vector space. I can take rho of T to be complex conjugation. And then what is the set of intertwiners from V to V? That's the set of linear transformations of the form Z to RZ, where R is a real number, and that's isomorphic to R. Example 2. Let's take M2 minus. Now, to write an irreducible representation, I need to take C squared. And how are we going to represent M2 minus? So phases are just going to be multiplication pointwise. And rho of t on z1, z2 is minus z2 bar, z1 bar. You see that's antilinear, and indeed it squares to minus 1. So I'm supposed to end in 2 minutes, I think. Okay. So rather than go on to the next section for B, complete reducibility, let me explain this a little bit more. So let's try and calculate that intertwiner, that space of intertwiners on this representation. Okay, so what do you have to do? You have to find the C-linear maps which commute with all the operators like this and the operators like that. So here's a trick. Here's a trick. Let's identify H with C2 by the other way around. Let's identify C2 with H by taking Z1, Z2 and turning it into the quaternion Z1 plus Z2J. By which I mean, if I write this out in terms of its real and imaginary parts, x1 plus y1i plus x2j plus y2k. Okay. Now, what does that by me? Well, you see, now rho of e to the I theta, in terms of operators on H, is cosine theta plus sine theta times left multiplication by I. And rho of t is just left multiplication by j. Okay? Now, anything that commutes, okay, any intertwiner, is going to commute with all linear combinations of these operators and products of these operators. In other words, the intertwiner must commute with the algebra, I'll call it rho of G, generated by these two guys. But now you see, you have a lot of freedom. You have theta, L of I times L of J is L of K. You should believe that that algebra is the full algebra of operators L of Q. Left, you can basically, out in this algebra, you can multiply on the left by any quaternion Q. Now, what's going to commute? Okay, what linear operator, real linear operator on, complex linear operator, so it has to commute with I, L of I, that's going to make it complex linear. What operator is going to commute with the full algebra but generated by L of Q? Any guesses? Pardon? Absolutely. You see, the left moving, my brain, the wires of my brain got crossed again, left moving. The left acting operators, left acting action by quaternion Q1 and the right action by Q2 clearly commute. Okay? And nothing else does. So the set of intertwiners in this case is isomorphic to H op, the right acting quaternions, which is isomorphic to H. Okay, so now I've shown you in example 1 and example 2 how indeed in Schur's lemma for G phi representations, for Z2 graded representations, I've shown you how you could get a set of intertwiners which is just R, or a set of intertwiners which is just H. And of course, if we have standard complex linear irreducible representations, then we're very familiar with the intertwiners being the algebra C. So now you can see that you really do get R, C, and H. And tomorrow I will continue with the outline, finish up the representation theory of Z2 graded groups, and talk about Dyson's threefold way, and I'll cobble together some incomprehensible statements about the tenfold way if there's any time left. So, thanks.